chemical analysis. So remember we talked about what does the chemistry look like when we get it from a lab, and we looked at some different cases. So this is where we looked at a really simple end member analysis. So this is what comes back from the lab. It's a sulfide, so we get iron and sulfur compositions. And we talked about how do we rationalize this chemistry with this formula. That's the point of this calculation, is to kind of connect this chemical composition with these formula units. Okay, and so we looked at a case where we had a sulfide, very simple, no solid solution. Then we added solid solution in. So we have, right, the sphalerite structure has a zinc position and a sulfur position, geometrically different positions in the crystal. And the zinc position can hold iron, cadmium, and zinc, and this one is all sulfur. And then how do we, come up with an exact chemical formula? I mean, this is the idealized formulas for sphalerite. Given this chemical analysis, how do we rationalize where things go into this formula and how things work out? And then we did we already did the olivine, didn't we? Yeah, okay. And so then the third case was where we are looking at a group where oxygen is the dominant anion. So in that case, usually, and this is for most geological materials other than sulfides and arsenides and things, you've got oxygen as the dominant anion. So the lab is going to report to us compositions as oxides. And how do we rectify these oxides then with this formula? Right, this is the dummy formula for olivine. So there's an M site, that's an octahedral site, a Z site, which is a tetrahedral site, and then the oxygen. And so when we look at the elements we have, we've got to decide which one goes in which position. The silica is small and has a high charge. Because it's small, it's going to go in the Z spot. The others are all about the same size. They like octahedral coordination because of their size relative to oxygen, right? The radius ratio would tell us that they like to be in that spot. So these three end up going in the M site. We've gone through the calculations then. So the difference with this one is rather than using atomic weights right here, we're using molecular weights. So we take the weight percent, which we could just think of as how many grams out of 100 of SiO2, and we're going to divide that by the molecular weight of SiO2, which is the atomic weight of silica plus 2 times the atomic weight of oxygen. It's basically the equivalent of the atomic weight, but for this molecule rather than for a single element. And we do that for all of these. So the FeO is just atomic mass of iron plus the atomic mass of oxygen and so on. We're going to take this column divided by this column. This gives us the number of moles of these molecules. All right, so there's this many moles of SiO2. And then we want to figure out, okay, we know how many moles of this cation or of this molecule I have. How many silicas, the cation proportions then, the proportions are the relative ratios of these things. Of the cations, we need to look at how many cations are contributed by this molecule. And as I said last time, this is a quirky case in the sense that these all have just one cation in these oxide species. So this column is exactly the same as this column. If it was K2O, it'd be twice as many cations in there. And then we do the same for the oxygens. There are 2 oxygens in silica, so this is twice as big as this. one oxygen for every one of these molecules, so they're the same. So this is the total number of oxygens, right? And this is the total number of each of those cation species, and they're all in the proper proportions for this particular mineral. Now we need to set those proportions up so that oxygen equals 4. Right, so we're going to recalculate everything on the basis of 4 oxygens. If the formula unit had a 6 here, we'd do 6 oxygens. If it was an 8, like the feldspars, we'd recalculate it on 8 oxygens. So that's where the 4 comes from. So we just have to ask the question, this times what equals 4? And that's the multiplier, right? You just figure that out with a simple algebraic expression. This times x equals 4. What is x? That's x. Okay, and then we take this and multiply, right? That's going to give us 4 oxygens. So the oxygen column now becomes 4. And now we're going to look at all the cations. So you multiply this by that, you get 1. Multiply this by that, you get this number, and so on, right? And then when we look at these on the basis of 4 oxygens here, the proportions of these things should fill in the rest of the formula nicely if it's really that mineral. So we have, for every 4 oxygens, we have 1 silicon. And that number is almost dead on. And for every 4 oxygens, we should have 2 of these. And when we add these guys up, they're 1.994. They should equal 2, which is good. Okay, so now we have this chemical analysis reframed in terms of that formula. All right, and so there are other ways to express the composition of this mineral. Simplistically, we can write down the chemical formula from these numbers, right? Mg 1.81, right? That's Mg. Fe 1.75. We got it from there. We're just going to round the silica off to 1 since there's nothing else that's competing with the silica, and the oxygen at 4. And we just threw out the magnesium because it's a number that's way less than 1%. All right, so here it is again. This is one way to express the composition of that particular olivine. The other way to do it is by using the end members, phosphorite and phthalate. Phosphorite is the Mg end member, phthalate is the Fe end member, right? So we can just take the proportion of these 2 elements, right? This adds up to 2, and if you take this and divide it by 2, that gives you the percentage of the phosphorite end member, and this gives you the percentage of the phthalate end member. And since phosphorite and phthalate add up to 100%, we can write it as just phosphorite 91. So we can simplify all of this chemistry down to just that. And most other mineralogists would understand what they were looking at then. It's a single olivine crystal that has a solid solution between the iron and the magnesium end member that's 91% phosphorite. All right, and so I think this is where we left off maybe last time. Frequently in journals we'll have the analyses and they'll do the recalculations right below. So this is basically jumping from this step to this step without putting all of the stuff in between. And they'll do that right in the journal to show the stoichiometry of the mineral. And then here's the phosphorite and the phthalate composition. So in this case, we have minerals that go from very magnesium rich to very iron rich at the other end. All right. I'm going to give you a homework assignment to do that will kind of walk you through that on your own. We'll worry about that after Friday, so it'll be after Thanksgiving. I'll probably hand it out on the Monday before we go back. but you're not responsible for this on this exam. But there will be a problem like that on the final. Graphic representation. So these analytical methods can allow us to collect a lot of data, right? I mean, we just dealt with one analysis, one data point. A microprobe can produce an analysis every 3 minutes. And so you can book 5 or 6 hours on a microprobe at $100 an hour. And you can produce literally hundreds of data points of chemistry. And trying to deal with all of that is just numbers, is just overwhelming. So we have to start to be able to look at the range and compositions of things in a graphical method. And so that's what I want to talk a little bit about, is the graphic presentation of these compositions then after they've been calculated by that method. Okay, and so we can look at plotting up things in a binary plot to start with. So here's a very simple composition